We saw in the last demonstration that HC logic was very good even with a lot of noise on the signal. We could put noise almost up to half the total size of the signal, and a standard gate would be able to tell what was a high and what was a low. And if we had noise that even exceeded half the amount, we could use a Schmidt trigger input and still be able to get good results. Now, if the noise gets too big, I mean, if the noise is bigger than the signal, neither an HC or an HC Schmidt trigger is going to work. But there is a technique to transmit signals, digital signals, in huge amounts of noise, and that's called differential signals. And what a differential signal consists of is a transmitter. We have a transmitter here. This transmitter has a digital signal going into it. It takes that digital signal, converts it into two signals, one that is in phase with the original signal and the other that's out of phase, so that one is going positive when the other is going negative. That's known as a differential signal. It actually uses much lower voltage than the input. The inputs are 5 volts, but the output is fairly low, and part of the reason that it's fairly low is it allows it to operate at very high speed. And at the other end, we have a receiver. This receiver gets the differential signal and converts it back into a normal 0 to 5 volt signal. So what we have here is LVDS, low voltage differential signaling, and we use that where there's an enormous amount of noise. So let's take a look at how that works. Once again, I'm using the function generator to generate my noise, and I'm going to use a sine wave. But this case, my sine wave is going to be much bigger than the signal itself. It's going to be bigger than 5 volts. And we'll see that we can still transmit a signal. Let's go up to our oscilloscope. See, yellow is our input signal. It's a 0 to 5 volt square wave at about 200 hertz. Blue is the output of the receiver. It's a 0 to 5 volt square wave. It looks just like the input as you'd expect, but what we see in the middle are the two differential signals. We can see the one in purple that's in the same phase, i.e. it goes high when the input goes high and low when the input goes low. And we can see another in aqua that's exactly the opposite phase. Those are our differential signals. And the reason we like differential signals is noise normally adds to both signals equally. So if the noise is positive, both signals go up. If the noise is negative, both signals go down. If we subtract the two signals, if the noise is equal on both signals, it goes away. But the signals themselves, being differential, tell us whether the input is high or low. And you can see it's working just fine now. We don't have any noise, but we're going to add some. So I'm going to add 1 volt of noise. So my differential signal channels are, channel 1 is 5 volts per division, channel 2 and channel 3 are 2 volts per division. I've got 1 volt of noise there. You can actually see the noise. And you'll notice that the output and the input look the same. Now let's start adding some serious noise to this. I've added 2 volts of noise. That's 3 volts of noise. That's 4 volts of noise. That's 5 volts of noise. So now the noise that I've added is just as big as the signal. But the differential receiver can tell what the signal is because the noise is the same on both signals. If you subtract the purple signal from the aqua signal, the noise, which is the same on both of them, goes away, but you can see that the aqua signal here is low, the purple signal is high. If you subtract them, you get the difference between them, and that tells us the output is high. Now, I can go ahead and add even more noise. Let's see, we've got about 2 volts per division, so we've added about 4 volts of noise there to both signals, and yet the output and the input are both the same. In fact, the only thing that limits the amount of noise we can add is the fact that the transmitter and receiver are both operating on 5 volts, and there's limits to how big the input signals to both of them can get before they won't work anymore. So this is quite impressive, and it allows us to operate digital systems in very noisy circumstances. Typically, these are used where there's a long distance between one signal, the output, and another signal, the input, and you're running wires along long distances. They act as antennas and they pick up noise from motors and lights and other electrical equipment. And if we tried to use just a single wire, non-differential, and ground, that noise would overwhelm the receiver and we wouldn't get reconstruct the original signal. But with a differential driver, we can get very, very good noise immunity. The downside of the differential driver is that they're expensive and you need to run twice as many wires, so you only use them where you actually need them. But you can see that when you need them, they work very well.